All right, good afternoon, everyone. Just an announcement at the top regarding quiz submissions. I'll look through some of the quiz submissions. Just want to make sure that everybody got their submissions into the Gradescope app. I just want to explain briefly again what it is. It's not an AI tool. There is no AI tool that's grading this. This is simply a computer-based tool. Instead of writing by hand, it's mouse clicks. That's all it is. Okay. But in order for that app to work, it needs to know where the answers are located. So at the instructor's end, at my end, I create this outline and I say I have like 5, 6 questions in this assignment. And when the students upload their submissions, all the students are doing is they are saying to the system, hey, this is question number 1. This is my answer to question number 1. It's located on page 1. So you require 2 clicks for each answer. Okay. So if you have 6 questions, it's 12 clicks at the student's end. That's all it is. And then when I sit down at my end, I'm going through it and I have the rubric and I do a click. Okay, everything correct, everything correct, everything correct, everything correct. If there is anything incorrect, and I just, again, mark it accordingly. Okay, that this is incorrect. And that's all it is. So it is very important at the student's end to ensure that you have noted down and matched every single answer to every single question. Let's say I'm grading 10 questions in the assignment and student has only 9 out of 10 matches. Well, they forgot or maybe they omitted number 7, and then I enter the grades for number 7. Well, the student's assignment does not have a space for number 7. They would not receive any of the points. So please, I'm trying to make sure that everyone understands this. Okay. All right. We'll begin. Oh, not that window. Oh, but since I bring up the window, this is something we were talking about in the previous class, voltage, power delivery between like four different power outlets. How many of you have seen this before? These have been available in the market for a long time. So we were discussing connecting loads in parallel. So this was a real life example that I brought up, that you can have multiple loads connected in parallel to the same voltage source and what it does to the power rating and the requirement. So these have been on the market for several years. You have AA and AAA batteries with built-in USB ports. You don't need a fancy charger. You can simply plug it into any USB adapter you want, and it charges up. There's a built-in circuitry right on top of each of those batteries. Okay, so if you ever need rechargeable batteries again, you might want to take a look at these. And these have become incredibly cheap. This is 8-pack for less than 20 bucks. Don't need to keep track of anything. However, I would not recommend plugging it into your laptops or your desktops. If something goes wrong, you don't want it blowing out your expensive laptop ports, right? You connect it to any battery adapter, like standard USB port, and it'll work. Anyway, the point, as I'm stating, you see all of these are connected to one single USB port. So they're all being diverted. Like, so it's splitting into 4 different ports. And every battery is now connected in parallel to that same USB port. So the question we were dealing with is, if you have multiple loads all connected in parallel, what does it do to the power requirements? So you don't want to plug this into your laptop or your desktop. More importantly, look at these. I have a sample of these too. It's like a flash drive. Simply take the cap off, plug it into any adapter you want. But the capacity of these is a little bit less because that USB port takes up a lot of space. So I would not recommend getting these. Okay, these would be better because the capacity is larger. And because it's lithium ion, it's gonna last for a long time. So anyway, let's get back to our lesson. Let's get back to our lecture. Where was? Okay, here. All right, space charge region and the depletion region. Okay, So as a quick recap, we have a p-type semiconductor, we have an n-type semiconductor, and then we bring them into contact. And so when you bring it into contact, there is a gradient that appears in the charge concentrations, right? We have this gradient that appears on either side of the junction. One side has a plethora of holes, the other side has a plethora of electrons. And in a bid to even out the distribution of these charge carriers, they diffuse through that junction. Okay, holes move from left to right, and electrons are going to move from right to left. They're diffusing through the junction. Now, when the electrons in the holes move through the junction, they are leaving behind ionized atoms. And when they leave behind ionized atoms on both sides of the junction, there appears a charge in that space. And these charges are localized because they belong to the ionized atoms. They are fixed in the structure. They cannot leave their position. Okay. So when electrons move, you have moving, actually from your side, electrons are moving from the right to the left. They are leaving behind the positively charged donor atoms. And on the p side, the holes are moving towards the left. They're leaving behind negatively charged acceptor atoms. So now you have positive charges here, negative charges here. They are localized and they're fixed in that space. And because they are fixed charges in that space, it is now known as the space charge region. More commonly, this is known as the depletion region because it is depleted of mobile charge carriers. It is depleted of free charge carriers. Free in the sense is the freedom to move. Okay. Whenever you hear or read the words free or mobile, in this context, it means they are free to move. So it is devoid of free charge carriers because they have all crossed over the junction. Okay. So movement of holes and electrons takes place due to diffusion. This movement gives rise to the space charge region because there is this space, because there is charge of positive charges on one side and negative charges on the other side. It sets up an electric field in this region that is completely devoid of all charges or all free charges. Hence, it is also known as the depletion region. So there are two contradictory terms in there. One is the space charge region because it has charges. On the other hand, we also say that it's depleted or devoid of any charges. Well, the charges that are present are immobile. Those belong to the donor and acceptor atoms. And the depleted charges are because of the holes in the electrons that are no longer present in there. All right, so hole diffusion, electron diffusion causes the space charge region across the metallurgical junction. If this continued unabated, meaning if there was no stop to it, then the PN junction would no longer exist. All the charges would be distributed equally, right? But this electric field is set up to oppose further diffusion of these charges. So after a certain point, this electric field reaches a level where it is now competing. It establishes a competing mechanism that opposes further flow of electrons and holes. Okay, so we have the space charge region, that's positive charges on one side, negative on the other side, establishes an electric field. And that electric field, let me actually go to the next slide, this one. So this here is shows us the total number of charges that are present. This is showing us how deep into the N-type material it goes, and this is how deep it goes in the P-type material. Okay. So N-type and P-type. Because again, remember, electrons are going to the left, holes are going towards the right. So there is a space charge region. You have charges appearing on both sides. Important to remember, because of the disparity in the doping, the number of electrons, number of holes is not the same. However, the total charge that is established is going to remain the same. So if you add this up, we're going to get minus QNA times the distance it diffuses into the p-type material. That is going to equal the number of charges in the N-type material. Okay. So the total number of charges, the charge density is equal. Doesn't matter what kind of, what the dosage is on both sides of the material. It could be 10 raised to 17 and 10 raised to 16. It could be 10 raised to 17, 10 raised to 15, 10 raised to 20, and 10 raised to 10. Does not really matter. Charge density will always remain the same. Again, remember the original purpose, the original reason why it's diffusing is to even out the charge distribution. So the charge density remains the same on both sides of the junction. And the charge density, integrate, and we can obtain an expression for the electric field. The maximum charge is at the junction, because as it goes away from the junction, it's going to go to 0. Okay. So you get E of X here. You integrate E of X to get the voltage or the potential. And this is noted by many different forms. I'm going to stick with the one that our book uses, which is phi, the Greek letter phi, PHI, lowercase. And phi X is known as the built-in junction potential. Okay, built-in junction potential. And this is observed, sorry, not phi X, phi J, which is this. And just to give you a hint of what's to come next, phi J is the voltage that is required to turn the diode on. Okay, this is the voltage that is required to turn the diode on. All right, let's go back here. So in summary, the process is you have doping on both sides. You have donor atoms on the N side. So you have plethora of electrons or excess of electrons. You have acceptor atoms on the other side. So you have holes or excess of holes. And then when you have both of them in close contact, it forms a junction. Because of the disparity in the doping and the presence of the charge carriers, a diffusion current is established. A diffusion current, again, is established due to the carrier concentration gradients. Okay, because they are moving and they're diffusing through the junction is going to give rise to localized variations that are fixed in spot or fixed in its space. Hence, it is also known as the space charge region. This disparity of charges on both sides results in an electric field. This electric field establishes a competing mechanism that opposes any flow of further charge carriers. And so we represent this P of X. X simply notes the distance into the N and P type material. Okay, X-axis literally, that's what it means. So it's the electric field, how far into the junction it extends. Okay. In the N type, we refer to the Xn, and the P type Xp. Put together is the size of the junction. In fabrication terms, we can accurately predict how deep our junction would be. Remember, in fabrication, the process of introducing impurity atoms is either diffusion or ion implantation. Diffusion is simply heating it up, so it diffuses into the material. So we don't know how far it's going to go unless we calculate that, right? If you simply just heat it up and just leave it, we don't know how far it's going. But greater minds have come before us. They have performed these experiments and they have determined these equations. And so all we have to do is we take these equations, we add in our dosage, we add in our temperature, and then we can accurately predict how deep into the surface it's going to go. So we can predict Xn and Xp. Okay. And those are the equations that we'll look at today. All right. So this electric field, and to complete our summary, this electric field is in direct opposition to the carrier. So it acts on the carriers. Carriers in this case, again, they all simply refer to both holes as well as electrons. Okay, they are charge carriers, so they refer to both holes and electrons. And so, as stated previously, the movement of charge carriers in response to an applied electric field results in a current. That current is known as the drift current. Okay, so the electric field gives rise to a drift current, and the drift current plus diffusion current results in 0. Because this drift current is a competing mechanism, the result of the competing mechanism. Okay. It all results from the act of introducing impurity dopants into our semiconductor material. All right, let's take a pause, let that all sink in, and let me know if you have any questions before I move on. Okay. No questions. All right. Why does it keep doing this every once in a while? So depletion region width. What is the width of the depletion region? So this equation describes the width of the depletion region. It's not okay. Go ahead. So question being asked is about the electric field. Does it go from the N region to the P region? And the answer is yes, it extends in both regions. Positive charge in, so the electric field is pointing in the direction of the P type. So I think, let's see, one of the diagrams, I should have that. Oh, come on. Yep, here you go. Yes. right? Positive on the right, negative on the left, pointing towards the left. Okay. WD0. W for width. Actually, it's lowercase w. So let me. Lowercase w is also used for energy, so let's not confuse it. Okay, WD0 is the width of the depletion region. All right, somebody who's online, please send a test message. Make sure Zoom doesn't kick us off. All right, thank you. Let's see. Let's send a message every 10 minutes. Don't know what Zoom might do. Okay, all right. So let's take a look. Xn and Xp we established is the distance of the junction depth into each one of those respective regions, right? So the total depletion region is comprised of a little bit of Xn and a little bit of Xp. How far into the N and P type regions is diffusing through? Okay, so Xn and Xp. Xn is the portion that's in the N type. Xp is the portion that extends into the P type. Okay. And then, as I stated earlier, it is a result of doping. This is something that we control. Na and Nd is the number of atoms that are introduced into our semiconductor material. So Na and Nd will be provided. You will know Es, sorry, not Es, epsilon S is the permittivity of silicon. Okay. Epsilon itself is permittivity. Okay, permittivity. Epsilon S of silicon. Permittivity of any material is given by epsilon 0 and epsilon R is absolute permittivity. It's a constant. Anyone remember what this is? No, not quite. 8.85, 10 raised to minus 12. The reason I bring this up, no worries, as long as you take a stab at it. The reason I bring this up is because, and there are many reasons why they use different unit prefixes, but most of these quantities is always referred to in centimeters. So when they first started up, we were still, we were far away from the current state of the art, which is like nanometers, right? Even like a few hundred micrometers was a big deal, right? So everything was related to centimeters. So our dosage till this present day and age, we still specify in centimeter square or centimeter cube or per centimeter square per centimeter cube. So in the book, the constant is labeled as farads per centimeter. It's 10 raised to minus 14 farads per centimeter. So be careful of the unit prefixes. When I was a student, I made these errors all the time. I would, sad to say, even sometimes, even today, when I'm in a rush, I might sometimes just do centimeters, and then invariably my answer ends up being incorrect. What I like to do is I convert everything down to, I convert all unit prefixes. So if it says millimeters, I will raise 10 raised to minus 3. If it says microns, I will put in 10 raised to minus 6, and then I will perform my calculations. Okay. It's just a personal way that I try to avoid and minimize errors. Does everyone understand what I'm saying? In the book and in the online system, when you enter your answers, it's going to ask you for centimeters. So be very careful when you're entering your answers. Okay. In a quiz or an exam, I leave it up to you. I typically always give my answers in 10 raised to minus 2, 10 raised to minus 3, and then meters or whatever. Okay. I tend to avoid using unit prefixes. That way I know exactly what my values are. Anyway, so absolute permittivity is a constant 8.85, 10 raised to minus 12 farads per meter. Book uses 10 raised to minus 14 farads per centimeters. That was just a quick note about being careful for unit prefixes. And then epsilon R is the relative permittivity of the material with reference to the permittivity of free space or absolute permittivity. Okay. So it's a ratio, it's unitless. Okay. For silicon, it is 8 point, not 8, it's 11.7. If I remember correctly, I thought I had it. Okay. For silicon, it is 11.7. Okay. You probably recall another famous equation using epsilon. Anyone remember from circuits 1? Well, yeah, that definitely, but I was thinking more in terms of like capacitance. Capacitance C is given by epsilon A over D. Where A is the cross-sectional area of the two plates, and D is the distance between them. And epsilon is again epsilon epsilon 0 times epsilon R. Okay. So permittivity, basically how much charge can we occupy? There's a point to this. Because we have charges that are stored on either side of the junction, this can be modeled as a capacitor. So every single diode has a junction capacitance known as CJ, CJ0. There are special diodes that are used as voltage control capacitors known as varactor diodes. VARACTOR, varactor diodes. Okay. So again, because there is charge that is stored in that junction, we can model it as a capacitance. It has a technical name. It is known as the junction capacitance. If we simulate this in SPICE, it is known as CJ or CJ0. It's one of the parameters we can specify in SPICE. Okay. And that's why it appears in that equation. So it's 2 times epsilon S over Q. Q is unit charge or 1 unit charge. Epsilon S, as I said, is the has to do with the capacity to store charge. And then you have Na and Nd. These are basically the doping parameters. Okay. And then we have phi j. Phi j is the built-in potential that develops across that junction. And that is given by Vt log of Na/Nd over Ni square. Ni is the intrinsic carrier concentration. For silicon, we typically take it as 10 raised to 10, unless otherwise stated in a problem. Right? Standard room temperature, so standard values for Ni. All right, let's take a pause. Let me know if you have any questions before we move on to the example. Okay. All right. Let's see. All right. So calculate the built-in potential and depletion region. Yes, go ahead. VT is the thermal voltage. Thermal voltage is, again, it's known as the Einstein relationship, KT over Q, which we had on one of the previous, in one of the slides in the previous chapter. Okay, so the question, problem statement is calculate the built-in potential, meaning phi j, and then the depletion region with WD0 for a silicon diode. Calculate Xn, calculate Xp, and then calculate a value for the electric field Emax. Doping concentration, the doping profile is given to us. Na is 10^17 atoms per centimeter cube, and Nd, donor atoms, is 10^20. Now, in the problem statement here, because you're doing the first time, I have it in the bracket saying it's in the P type or the N type, right? But I mean, even if I didn't state it explicitly, assumption would be that acceptor atoms are going to create a P-type material, and donor atoms are going to create a N-type material. Again, when I was a student, the way I tried to train myself to think of it was donor means I'm donating an electron. If I'm donating an electron, it's an excess electron, so N-type. And A is accepting electron, because I'm accepting electron, now it's positive, and so it's going to create a P-type material. Okay. All right, so let's calculate. We need, what do we need? We need NA/ND. We need phi j if we wish to calculate WD0. So let's go back to this equation, right? What do we need? We need epsilon S. Epsilon S is something we can calculate, right? That's going to be a constant because it's silicon. We need Na, we need Nd, and we need phi j. For phi j, again, all I need is Na/Nd, but I also need Ni. And there is no mention of Ni anywhere in the problem. So what do you do? Yep, answer is that you calculate it. I was gonna loosely state we can just make it up. So we would assume room temperature or any other temperature, and we would calculate it. So yes, you would make it up by calculating it. And if you just want to assume, if you want to make our job simpler, we can just say, I am assuming Ni is 10^10 atoms per centimeter cube. Because at this point, intrinsic concentration in every semiconductor is very well characterized, right? It's a standard equation for intrinsic charge carriers. For specific temperature, it is very well known. So if it's a silicon semiconductor, we don't even need to calculate. Simply say we assume Ni is 10^10. So the point here is, if it's given in the problem statement, great. If it's not given, we make it up, or actually not make it up, we assume. So let's just assume 10^10. Now, thermal voltage is not given to us. We can calculate it. But in several of the examples, the book either uses 25 or it uses 25.86. But let's say, just for simplicity's sake, we just assume VT is 25. millivolts. Again, this is the voltage that appears in semiconductors due to the thermal effects. Okay, it's an integral part of many equations. Okay, so take out your calculators. Now that you have Na, Nd, Ni, and Vt, tell me what you obtain as the answer for phi j. You have the equation on the previous page, and you have you have the values here. So what is phi j? All right. What do you have? Point. I like that. I would, so chuckles aside, I typically would, if I am going to use a quantity for future equations, meaning in this case, I need to calculate WD0, right? By the way, did others obtain the same answer? Okay. All right. So the point I'm making is we have multiple decimal places going all the way up to 9, 10 decimal places, right? If I have to use the value for future calculations down the line, meaning in this case, I need to use phi j for WD0, I take as many decimal points as I can. This avoids getting different answers all the way to the end because it carries on down the chain. If I was to simply take only 2 decimal places, I would do 0.98, I would be done. Everyone see what I'm saying? But then I'm going to use it again for WD0. My answers might end up incorrect. More importantly, in semiconductor devices, we are dealing with the micro and the nano scale. So it matters how small we go with the decimal places. Okay, it ends up being a very big deal. And so you always want to take as many as you can. So if you take phi j now and you plug it into the equation for WD0, what do you get now? And then there are further equations I can give, I'll provide for xn, xp, and emax. So did somebody do a calculation? It's 11.7. So let me write it here. Actually, let's go back here. So for silicon, epsilon, sorry, not epsilon s. Epsilon s is epsilon 0 times epsilon r. Epsilon 0 is a constant. Epsilon r depends on the material. So for silicon, epsilon r, or relative permittivity, is 11.7. Relative permittivity is the ratio, meaning you're measuring the permittivity of the material with relative to absolute permittivity. So it's a ratio. And because it's a ratio, it does not have any units. It's dimensionless. Okay. So what do we have for WD0? Anyone? Did you raise your hand or just okay? I thought you were raising your hand. So anyone? Q is 1 unit charge, and so 1.6 into 10 to minus 19 coulombs. And so actually, let me write it here. 37. Wait. 1.6, 10 to minus 19 coulombs. So the purpose of this exercise is, again, we are working with a wide range of values and small numbers and lots of exponents. And so students need to be adept at making these calculations. On a homework is the time you practice doing these calculations, because you can get it wrong and still not lose any points. But in a quiz and in the final exam, it's a big deal then. No do-overs. And this is coming up in quiz number 3 next week. Okay. So again, anyone? What values do you have? Yeah. So tell me again, how many zeros? 1, 2, 3, 1, 1, 3. All right. The 1, 1, 3 is correct. But at my end, I had 0.113 times 10 raised to minus 6. Either my answer is incorrect or maybe I need to recalculate. You got the same? Yeah, that's right. The other students also saying the same thing. You got 0.113. Unit prefix, yes. So I'm getting 0.113 times 10 raised to minus 6. Here it's 113 times 10 raised to minus 6. So when you perform this calculation, we have NA and ND, right? And then the square root. So for both of them, it's 10 raised to 16, 10 raised to 20. No, 10 raised to 17 and 10 raised to 20. All right, so then I will take a look at mine. WD0, you're saying you're getting 113 microns. All of you are getting this answer? So I'll check my calculation, see if there's an error in mine. That is all right. One thing I know, 113 is correct. But as I said, I have 0.113 microns. 113 microns is a huge number. And so it will not be 113 microns. Okay. So I can say for sure it's not going to be that. Usually it's less than, it's like 0.1 microns or less. Is somebody had a hand? Yes. So it's 10 to 7. The question being asked is, do you convert it into meters? Yes. So if it's per centimeter cube and you convert it to meters, what do you get? How much do you get? If the density is 10 raised to 17 in a cube of centimeter by centimeter by centimeter, now it's multiplied 3 times. So it's, if you convert it to meters, 10 raised to 17 times 10 raised to 17 times 10 raised to 17. Anyway, we have limited time left, so I want to go over the equations for xn, xp, and emax. So WD0, once we have the junction width or the junction depth, a little bit of it's going to extend into the n-type and a little bit is going to extend into the p-type material. The extensions into the material is xn and xp. So the equations for those, remember WD0 is comprised of xn and xp because it's extending into both different types of materials. Xn is given by WD0 divided by 1 plus ND over NA And these equations are there in the book. So if I make an error, please let me know. WD0 over 1 plus NA over ND. Okay. NA over ND. And Emax is 2 times phi j over WD0. Okay. Does everyone have it? So 4 minutes left. Since everybody was trying it, an excellent point was made. We have the doping concentration Na and Nd in atoms per centimeter cube. So if I was to make, if I was to perform my calculations, I would, and I was converting everything to meters, then I would have to change 10 raised to 17 atoms per centimeter cube into meter cube, multiplied by 100, multiplied by 100, multiplied by 100. Did everyone see what I'm talking about? 1 meter is equal to 100 centimeters. So if I am defining 10 raised to 17 atoms per centimeter cube, now I got to multiply by 100 because I'm extending the dimensions from centimeters to meters in all 3 directions. So multiply by 100, multiply by 100, multiply by 100. Million, essentially. And see if that makes a difference in your answers. All right, let's see. Next slide was, what is next slide? Diode IV characteristics. All right, so if we plot if we plot a response of the diode current as a function of diode voltage, well, because of the built-in potential, there will be no current flow through the diode. Okay, because of the built-in potential, there is no current flow through the diode. The diode characteristics are going to be 0 until a certain level of voltage is applied across the diode to overcome that built-in junction potential. And that voltage is known as the turn-on voltage. Okay, it is known as the diode turn-on voltage. Simply also just referred to as VD, diode voltage. Diode voltage and diode current. Once the diode turns on, current increases exponentially. And so there's a sharp increase in the current. And this is something we saw in the simulation, in the PSpice simulation in the lab. Okay, it did not have as sharp of a curve because a graph was stretched out and we were only simulating up to 2 volts. If you run that same simulation all the way up to 10, 15, 20 volts, and the graph is squeezed, you will see it's the same exponential growth. Okay. Near the origin, the diode characteristics always pass through the origin. Okay, so for 0 volts, you have 0 current. So this is positive voltage. This is negative, and this is exaggerated. Okay, It's very, very small. And you will see this in lab 3. When you perform the when you apply, how many of you are done with lab 3, by the way? Anyone done with lab 3 yet? So when you did applied voltage in the opposite direction, which is reverse bias, you will not be able to measure any of that current. Did you perform the simulation with what is it, sweep and go? Did you all obtain? You might have obtained some current value from the sweep and go, and so those, yeah, that sweep and go is really good. Okay, we are at an end, so we'll end class here today. I'll see you all on Friday. If you're in my lab class, I will see you all tomorrow. Run the calculations again for xj, because again, as I said, my answer for WD0 is 0.113 microns. Okay, great. That's why these unit prefixes can be very tricky. You have to convert everything. As I said, again, the equations are straightforward, but trying to apply and calculate is a little tricky.